Math Colloquium. I'm very pleased to be able to hear a talk from Lior Horesh. So Lior has been at IBM for about the same amount of time that I've been at Cornell. We both arrived in 2009. He did his PhD at University College London. And he's both at IBM Research and is also teaching some classes at Columbia these days on quantum computing and on machine learning. I met Lior first because he was the chair of the last Mathematics and Data Science meeting that SIAM ran, and I was on the committee, and after interacting with him for a little bit, thought this would be a great guy to have for Camp Colloquium. So I'm very pleased that he's here and is going to tell us about sort of combining data-driven and theory-driven modeling for physical systems. With that, I'll hand it off to him.
I'm really delighted to be here today. It's the first time that I visit the campus, and it's beautiful. I hope that you will enjoy it. So I had a quick discussion with Earl earlier, and I'll share with you a personal story before I dive deep into this. So as a scientist, at some point, you have more gray hair coming than gray matter, and you keep on having those dreams about a Nobel Prize or a Turing Award or something of that scale, and the horizon keep on getting a little bit further from you as you see how somewhat limited you are in your capacity, ability, and where your dreams are, right? And then this is all ego-driven, right? It's my narcissism, right? I hope that not all of you are like me, but it's good to have aspirations. So sometimes in my midlife crisis, I was thinking, okay, how do we move forward from here? And I said, okay, let's admit, probably I will not be able to come up with Nobel Prize-worthy inventions or innovations just using this machinery, but maybe I can build a machine that can do it for me. Right? And this is really the story of what we are trying to do along those lines. And in one slide, I will try to summarize everything we try to do. And everything else is just details, but hopefully you will enjoy the details, not only the story. So imagine that you have some observation about the natural world, a process, or some other phenomenon. And you also have some knowledge. That knowledge can be articulated in formal forms. There can be some conservation laws, symmetries, and so forth. What you would like to do, if you have my ambition, is to put in this Nobel Prize machine or wonder machine, and that machine will do two things for you. Right? One, it will spit out fundamental relations that explain everything about both data and knowledge. But there are so many things that can just spit out different models. It's nice, it's useful, but it's not enough. You would like also to have maybe a derivation. How you can derive this relation from first principles. And then, if you can do both of these, the inevitable will happen, hopefully. And if that will happen, this is what I was sort of envisioning in my mind, right? So now I'm going to take this from the story of hopefully. And if there is a phone call in the middle, maybe from Oslo or whatever, I may have to pick it up, but probably not here. And obviously, this is not only me. Many talented researchers have been working on that, and very honorable funding agencies, so we thank them all. And now let's talk about science. So science is really our quest to understand the natural world through observation and reasoning. And Descartes and Francis Bacon, they were the two that effectively conceived the so-called scientific method as a principled way for us to do science. And they were at the beginning of so-called scientific revolution, we all, in one way or another, follow this sort of cycle and trajectory quite successfully, right? This has been transformative from a socio-economical perspective. The scientific method was really an amazing driver. I would maybe just comment that this is for later. René Descartes was one of the first to also observe that we need to also put some attention to deductive logic and not only to empirical evidence. We will get to that later on. But the beauty of this method is that really it enables us to devise some common principle practice as for how we make substantiated discoveries. And it all looks good, but lately people have been expressing concerns. And there are many studies, these are just 3 of them, but there are interesting studies describing that the rate of emergence of new discoveries is actually slowing down compared to the amount of effort, capital investment we put into those. And this is somewhat troubling, right? Because if you look into this graph, you can see the green line is normalizing in 1930 in terms of number of effective researchers that we sort of pour in, and the blue line is some measure of research productivity being realized. I think this one is called total factor productivity, but there are other such economic measures of productivity. And this is quite surprising to some extent. The great Paul Dirac was saying, it is now more challenging for first-rate physicists to make second-rate discoveries than it used to be for second-rate scientists or physicists to make first-rate discoveries. And in this book, The Great Stagnation, Cohen proposed maybe the scientific method has already picked up all the low-hanging fruits, and there's not much left for us to discover again with our brilliance, but still finite ability as humans. So one thing that we can acknowledge is that many of the challenges that we face today cannot be tackled by a single scientist. So Atlas lifted the universe at the time. That is not the right model for us to think about scientific discovery. It's the other way around. If you read *Sapiens*, and then what our maybe superpower as humans is our ability to collaborate flexibly at scale and to tell stories about it, build a narrative. And recently, this notion of collective intelligence become more and more prevalent. There are groups that are pursuing that, and it's really the art of bringing intelligence from more than a single entity. I would say not necessarily humans, but can be humans and machines. And we can see, and there are many success stories about us humans collaborating together, like Wikipedia and Foldit and CAPTCHA and so forth. These are mainly crowdsourcing type of efforts, right? So I believe in Foldit, they were trying to discover some biological structure that was related to AIDS in monkeys. They tried it for like 17 years. The University of Washington, they couldn't do that. They then made a game and opened it up to the broad audience, and in a matter of 3 weeks, it was solved, right? So there is power by joining forces. And then obviously, if we can somehow find a way to collaborate with machines, maybe we can do even more, right? Now, if we look into automation trends, I guess from the dawn of time, mankind was trying to find others to do his job, right? If there's one thing that we can characterize ourselves, we are lazy, and laziness is a great force of innovation. So we harnessed first animals to do our job. Later on came 4 industrial revolutions that kept on pushing the boundaries of what can be automated in terms of how complex the task is, right? So we are now capable of doing more and more complex tasks by the machine. And now some would say, we are at the verge of maybe some singularity or something like that. We are really getting to a point where those machines can match us, at least in some tasks, right? So this is really great or sad, depending on your perspective, but it is happening, right? Now, if we ask ourselves, okay, so what is left for us humans? Where are the highlands that we can run to? And you can argue about the order of the different cognitive tasks here on this pyramid. But what I was really trying to figure out when I started to do this work is what is more, say, is inspired or aspired? Is it creativity or discovery? What should be at the very top of this pyramid? And I guess now with generative AI, maybe we got the answer. Creativity as is great. Machines can do that pretty well. And discovery requires yet maybe a slightly higher level of a bar to cross, because at the end of the day, it's not only coming up with an equation, it has to be consistent with everything you knew and with the observations, right? And maybe future experiments that you're going to make, right? So that is slightly higher bar than, okay, I just created this funny picture. You may like it, you may not like it, but it is what it is, right? So discovery is an interesting task to perform, and now we can ask ourselves, what is discovery, maybe in the context of mathematical sciences. And I will talk about mathematical modeling. Mathematical models are a mean to find a consistent link between an input and an output of a process or a phenomena, of a system. And when we go into the art of modeling, we typically make some compromises between different attributes, how complex the model is versus how realistic it is. And there are other trade-offs that we may want to gauge as we do that, like interpretability and generalizability and so forth. But at the end of the day, at least traditionally, there were two camps that were trying to promote the field of scientific discovery. One is the first principle camp. The other one is the data-driven camp. And if we look a little bit more closely into each of them, the first principle modeling camp, we all know those names.
I did. Sorry.
We all know those names, right? These are really the giants of science, and we all stand on their shoulders. The elegance of the relations that they managed to discover is non-deniable, right? These laws are universal. Maxwell laws, for instance, these are four very, very compact equations that describe to you everything you ever wanted to know about electromagnetism and never dared asking, right? It's really beautiful. And not only, if we see his friend Einstein next to him, those four laws actually are even consistent under Lorentz transformations. So if you take an inertial system, those Maxwell equations are still holding. So how elegant and beautiful, can it be any more elegant and beautiful than that? Probably not. However, as you can see by dates, it may take some time to come up with something of that clarity and universality, and definitely talent. I'm not sure. You will not see my face as one of the very, very soon. And my role model for this line of work, because I'm not in the business of finding a Nobel Prize. People are asking, oh, what is the IBM business in this? A single Nobel Prize may not be really the right deal. So I'm really in the business of many of them, right? And our hero is Marie Curie, who was the first scientist to come up to receive 2 Nobel Prizes, one in chemistry and one in physics. Okay, so then what happens on the other camp, right? We have the data-driven camp, which, if you just read the headline, it looks very similar. You're attempting to find a link between input and output data by some generic functional form. Typically, the last part of this sentence is written very, very small, the disclaimer part. And you may ask yourself, okay, that doesn't sound too far, but of a generic functional form. And the reason we choose a functional form is because there are functional forms that we can exploit computationally, right? We are not idiots by virtue of doing that. These functional forms can be exploited very nicely computationally. And these methods are very effective when you have a huge amount of data and when you have little knowledge about the problem. So I have no other choice but to be driven by the data if I only have data. However, they may fail to generalize very well. I assume that many of us have seen that. And to be honest, if we already picked up the functional form before we ever saw anything, we ever saw the data, we cannot expect to look into the structure or the functional form of the problem and get a new insight about the problem that we are looking at. So not much of interpretational insight can be expected. The other thing is, we mentioned that large data, volumes of data, so collecting data can be very expensive, right? So here is an example. Right? Data doesn't come for free. I'll give you another example. This guy needs to go to a very remote site and collect the data, and sometimes he's not alone. You need to establish who is the... And even getting back home, sometimes it's not that easy, right? So we cannot assume that all problems are big data problems and that's it. The problem is solved by virtue of data-driven approaches. Now, what limits conventional machine learning? And sorry for trashing them. Both sides should be equally appreciated and trashed, I would say. Let's assume that we have the real behavior of a system or a phenomena that's the solid line, and then we try to come with a model, that's the dash line. And we start bringing in the data. So here is my staple. I will condition the model to the data at this point. That looks a little bit better, not much better. Let's repeat that process again. Okay, we are getting there. And then, how about here? And maybe here and here and here, and then, oh, that looks already not that bad. We have a model that is somewhat, at least at those points, on the data. Can we really make it any better? So one thing that you need to notice is that while I managed to get equality or close to equality at those junctions, outside that, I cannot really control it that much. So let's do what we typically do in data-driven approaches. Let's bring more data. So I bring now a better stapler. Here is my super stapler, and I bring much more data. But that doesn't really help me to resolve what's going on here. So there are excellent interpolators, but not that great of extrapolators as methods. Now, if we try to summarize maybe the virtues of both approaches, it's really not a clear picture, because whenever first principle methods are better, indeed the other are worse, but vice versa. So if you have glasses and you take them off, you'll see that you have green and blue in somewhat complementary form in this table. Right? So that brings the depth almost what happened to the time is out. Okay, now dance. Let me try to connect and disconnect, which is the first. We have computer scientists here, so I'll use that practice. And IT expert. Let's see. There was a signal for a fraction of a second. Let's see. Okay, let me try to smaller. Yeah, okay. I think that we will be okay. Oh no? Interesting. Huh. For the projector, you mean? No, but it seems to, the moment that's my screen, you may think that I have more than one.
Yeah, when it was all black, I still saw the mouse moving around. So.
Right. Let's see if we can. Now we just talked about working with the machines, and here you go, right? Okay, good. So the machine
it's not.
No, it's okay. I was trying to skip to where we are. I believe that we will be okay. We will be okay. Oh no, something about that slide. Oh, it's just a dark slide. Okay. You see how limited my gray matter is. Anyway, so that brings us to the question, should we derive or let the data derive? And I guess you all probably agree that probably should try to find the best of both of these. Why should we choose if we can have both? So that brings us to symbolic model discovery. And if you see the literature, you may find many studies that, in my mind, excessive effort in finding the very precise solution, asymptotically converging to the right, or seemingly the right place of the wrong problem. But it is indeed converging, right? So we have, as scientists, we have that tendency sometimes, and me, I'm guilty as charged many times. Now, how can we overcome this fundamental limitation of data-driven approaches? So maybe we should think about a free-form discovery. We should not use a generic functional form. We should have a free form, and that will also enable us to have richness in the expressive way of what is our problem or what is our model. And now you can say, oh, sure, free form, but if you have a cloud of points that maps to a cloud of points, there are infinitely many models that you can come up with that will satisfy that sort of mapping. And one resolution would be to say, okay, sure, but I'm trying to find maybe one that, on the one hand, would honor the data, but also maybe the simplest one. So I'm looking for the least complex one, and maybe I would like also to have some other virtues being honored as we do that. So what we have done in the first line of work, so there are 3 of them, was defining a grammar such that every meaningful mathematical expression is a sentence in a formal language where we have 3 different components, right? So one part of the language is operators. You see them in green. These are those exponents, plus and minuses, and so forth. Another part are the variables in orange, x, y, z, and so forth. And then the last one are constants. And if indeed we have that setup, the grammar can be encoded as a set of decision variables and constraints. And we can perform a free-form search for this in the space of sentences for one that honors the data, but also minimize some measure of complexity. Right? So that was the problem definition. And you can write it down nicely as a mathematical program, minimize the complexity of the symbolic expression f, where when you estimate that f at some datum x, it is close to the data in some noise model, and the model itself is sparse, is parsable, so it is a valid statement in the language. So x plus plus 5 is not a valid one. This is something that you can articulate, and so forth, right? So you can write this declarative form of a mathematical program, and you can try to solve it. We did it with mixed integer nonlinear programming, but there are many other ways to do that. So here's an example. So back in 1589, Galileo, I was unaware of that, but he was actually a medical student, and he was sitting at the Cathedral of Santa Maria of the Assumption in Pisa, and he was very focused on medicine, so he was looking at the chandelier swinging from side to side, and he was surprised that independent of how large the exclusion was, small exclusions or large exclusions for small angles, the time that it took for the pendulum or chandelier to perform a cycle was consistent. And at the time, unfortunately, he didn't have his iPhone or whatever to measure time, so he was actually using his pulse as the timer. But given that consistency, he actually then invented a simple pendulum for measuring time. So no longer need to use sand watches and sun watches and so forth, sundials. So we said, okay, let's do that. So we took and typically I would bring here, and I apologize, next time I come here, if I will come, and tell you about similar story, I will bring a wave pendulum. So this is a wave pendulum. So each one of the, it's several pendulums which has different link lengths, and because they have different link lengths, they may behave in a funny way. And here is an example. So you can see how it's really beautiful to watch it, right? Even if you start them all together, at some point they all start to wiggle in those somewhat hypnotizing form. And if you take the data for that, this is what we did. Now skip. We actually took the data only from 18 points. We wanted to be honest with small data. And I'll skip that because this is the first attempt. It took a lot of time. Now it takes less than a second to do that. But after a while, you put it in this framework, and then you get a symbolic relation that have this nice square root of L component, so the square root of the link length, and has this square root of G component that we also want to see. And you may ask yourself, okay, so why should I care? And if you compare this expression, here it is again, to, let's say, equivalent expression that you can get from a neural network. So that's the second expression you see here. So we have weights multiplying a layer entry plus some biases, goes to an activation layer that outputs into another weight, getting another bias, and so forth. Right? This is just explicitly writing what a neural network is doing. Obviously, I have very little interpretational insight from the second expression. Right? I will not be able to immediately understand that if I'm going to change, let's say, the mass of those balls on the pendulums, it will actually not have any meaning in terms of the period time. But on the other hand, if I'm going to change the link length, it will behave like square root of that. Right? So we have that interpretational insight, which is great. We then said, okay, let's look into Feynman lectures on physics. He derives 100 relations in that series, and we wondered whether we can discover them, and we managed to discover 87 out of the 100, but we actually managed to find 2 others from Jackson and Goldstein book for the physicists in the audience. I don't know how many of you are here. Okay, you surely know those books. And so some of the expressions are actually not that trivial, right? So we managed to do that, and we later on, and I regret not publishing it, we said, oh, can we also decompose the constants? And apparently that was more or less no-brainer because you can do that. And at the time, or many years ago, Gauss discovered just by computation the beautiful arithmetic geometric mean up to the 17 or digit, but at the time, or 11 decimal digit. But at the time, every time you manage to compute, let's say pi square, up to a certain decimal digit, you would write it down because there were no computers, right? Like it was really precious to compute something like that. So I actually have this book in my desk. Nowadays, you don't need those anymore. But thanks to Gauss, right, you can compute exponents and log and other functions very, very efficiently. But what we did was, you can now decompose even a constant into, let's say, some primitives, and assuming that there are some operators that connect between them, and the system will do that. Now, let's take the next step. So we are capable of doing symbolic regression, effectively, but we didn't really, other than maybe manually almost, bringing some knowledge in, we didn't really incorporate knowledge. And why is it important to incorporate knowledge? So Lior was engaging in doing complex calculations of discrepancies that he saw on Uranus trajectory, and it didn't make sense to him because he knew Newton laws, and the observations were inconsistent with that. And thankfully, he didn't say, "Oh, these are just measurement errors. Let's rest." He was trying to figure out what could explain that, and he came up with an understanding that maybe there is another planet, Neptune, that we don't see, or he couldn't see with his telescope, that can explain all of those discrepancies. And he sent a letter to his friends, the Berlin Fraunhofer refractor, the same night. They got it, they went out, and within 1 degree, they found Neptune, right? So that was an amazing triumph of being able to synthesize both knowledge and data rather than just relying on one of them independently. So when you look into these two sources of information, we may ask ourselves, okay, what are the properties of these? And data is very local, right? So when we talk about data point, we use the word point because it's really a geometric point. And we don't know about that point anything, right? So if you go epsilon away from that point, you would still have no clue what are the values. And on the other hand, knowledge, we had a nice discussion with Dexter earlier, knowledge is universal, right? Or can be universal, right? I can say something like, for all x's, y is larger than 17, right? So and now I told you something about the entire universe, right? It's not a point. So this is maybe one difference, but we often used to trash data. Oh, data is noisy, but or background theory or knowledge is pure, but it's not the case, right? So knowledge can be incorrect. You know about Newton laws are incorrect. Einstein laws are even incorrect if you so it's not nothing is cast in stone. Now we say that data is sparse, it's true, but also knowledge can be incomplete. That's maybe the equivalence of that, incomplete with respect to something that you're trying to prove. So imagine a set of axioms, you're trying to arrive at some theorem, and you miss one of them, good luck, right? So it can be incomplete. Data acquisition is expensive, we saw that. Knowledge acquisition can be also quite complex. And maybe the last thing that is important is when we talk about data, we typically, the language that we use are arithmetic operators. When we talk about knowledge, we actually can use formal logic as inference as the language to connect between them. And I was not an expert in logic. I learned much of it in the past few years, and I'm still learning. But if you want a quick refresher, right? So we can. There are different definitions. So axioms are basic assumptions and principles that do not need to be or being assumed to be correct without a proof. Literals are propositional variables, or the negation of which. Logical connectives are symbols that combine one or more propositions together to a more complex proposition, such as conjunction, disjunction, negation, implication, equivalence. All of those are connected, are logical connected. Resolution is one of many inference rules that helps you to produce a new clause implied by other clauses. And a theorem is a statement that has been proven using some axioms and definitions and so forth, and the proof is really the way to get to that theorem, right? So now that we have all of that, maybe we can talk about the same language. We can notice that typically when we do definitely statistical AI or data-driven type of discovery, we use a very limited language, right? We use variables, constant, arithmetic operations. That's the toolkit we all use. And once you bring in all of those other elements to the game, you may be able to do more. And now I'll describe to you the first system that we use, or maybe the second system that we use, is called AI Descartes. And the general idea there was as follows. You have some data, you may have some modeling primitives, you need to define that grammar, and so forth. You bring all of that together and you come up with a symbolic regression expression. So you have multiple hypotheses that are consistent with your data and the language. And now what you would like to do is to say, okay, but different hypotheses, which one of them is consistent with my knowledge? Let's say conservation of energy, conservation of mass, conservation of angular momentum, symmetries, and so forth, right? So I would like to bring them all in, use a reasoning engine, like an automatic theorem prover, and if indeed I have complete background theory, I will be able to get the derivation, but otherwise, at the very least, I will be able to re-rank my hypotheses according to how consistent they are with my background theory. So it's no longer just a set of multiple propositions that are matching the data approximately well and are equally complex, but I have some mean to order them. And then, obviously you can get some substantiated discovery. So really very, very briefly, when we talk about reasoning, you have some background theory and that comprises multiple axioms. And often you would come with a conjecture that you would query about. And then the reasoning engine can provide you one of two things. Either it will perform just consistency checking. Is it consistent with that background theory? Or it can even do more than that, validation, which effectively shows you how from those set of axioms you can derive the new conjecture. Now, there are good reasons why we didn't use all of that machinery so far. First of all, I mentioned, logic is not perfect, it can be inconsistent, it can, and then maybe we can figure out what is inconsistent, but it can be inconsistent. We may lack all the background theory, typically we do, and that's another challenge, but also computationally. Theory provers are computationally quite demanding, and that is maybe an impedance. So some of the objectives that we had for that system were articulated here. So first of all, we would like to be able to establish if a given hypothesis is derivable from background theory. If it's not, we would like to have a counterfactual. I would like to give you an example where that fails. That can also be useful because then I can eliminate that one and be happy and without any regrets. If we have some constraints upon the functional form, I can also impose them by virtue of doing that. But maybe the last one is the more interesting one, because in logic, we typically have a very, let's say, a polarized, I'm not sure that's the right terminology, but a very black and white type of way of thinking about problems, right? It's really the elegance, is the consistency and how clean it is. But on the other hand, we do want to talk about, again, incomplete knowledge and incomplete data, noisy data. So we would like to be able to think about a notion of a distance from a derivable form, right? So imagine that I have a manifold that describes conservation of energy and another manifold that describes conservation of mass, and there is maybe some there is some overlap between them. That will be there can be so many hypotheses that lie in that interface, and I would like to ask, here is my hypothesis, how far it is from any derivable form, anything that is consistent with these two, or four or whatever, sets of axioms. And that notion of maybe, if we typically talk about model quality, typically we talk about the fidelity and the complexity of a model. We have this nice Pareto curve where we can put different hypotheses. Now we would like to have another dimension where we ask not, yes, is it derivable, not, it's not derivable, not a binary qualification, but we would like to have a more continuous, how derivable, how close to derivability it is, and that was what we were trying to establish in this work. Maybe I'll just be brief. So there are different methods and systems to perform a logical inference. One of them is based on cylindrical algebraic decomposition. I will not go too deeply into the machinery, how this is being done. It's actually very, very elegant and very nice. But if you are curious, I'm happy to explain that later on. But let's see how well that works. Right? So here are three examples. The first one is the Kepler's third law of plenary motion. Then we have Langmuir absorption equation, and then Einstein time dilation. Each one of them introduces different types of challenges. So on Kepler, we had very few data points, less than 10. Right? Try to train a neural network of 10 points. I don't think that any of us will claim that they can do that. And another challenge was that the scale, right? So the mass of a star versus the mass of a planet can be 6 orders of magnitude different, and typically we just regard that other mass as a noise unless you bring in theory. Langmuir is challenging because it contains material-dependent coefficients and also constraints about the functional form. And Einstein theory, we wanted to contrast two different systems of axioms and see which one of them would be consistent with real observations. So Kepler's third law of plenary motions, for those of you who remember, effectively predicts what will be the period time for a planet to orbit a star. And this is the expression that we have. It depends on the masses of both of them and the major x's, that's this b cube, and square root of all of that. And here is a description of how background theory of such a thing may look like. I spoke about background theory, here's an example. And now, really in a very cartoonish way, we look into three data sets. One was the solar system, our own solar system. The other one was NASA exoplanet data set. And another one was a binary star data set. And first you just perform symbolic regression, and you can get multiple hypotheses from each of those data sets, or you can combine them somehow if you want. But if you just follow that, you may be, I would say, fooled to believe that the model that performs best is not the model that is actually consistent with the background theory. The moment you bring the background theory into the game, you can actually and introduce this notion of reasoning error. So how far you are from being derivable. So let's look into, for instance, if you just look into the numerical error, as we typically do, this model would probably be the winning model. It looks terrible, but it fits the data beautifully, right? Now, if you look into the reasoning error, how consistent it is with background, with derivation of background axioms, actually this model seems to be much more consistent. And if you look into the expression, again, this is from real data and partial knowledge, it's not the entire knowledge, you get something that, other than 0.996, if you just replace it with a 1, that's the true model, right? So you have another lens to see through different hypotheses. As for Langmuir absorption equation, so this is an equation that describes you how chemical processes, how gas molecules are contacting a surface as you increase the pressure. And it's a little bit like filling up an auditorium room, right? At the beginning there is so much space, so it's very easy to find a spot, and then at some point it becomes harder and harder because all the spots are taken. And here again, you can come up, okay, here is the background theory, but we also had some constraints upon an unknown functional form. So for instance, we knew that the derivative, for instance, it's monotonically increasing, right? So the function is monotonically increasing. And you can incorporate some of those bits of knowledge in the game and the background theory. And then using that, so first you can do symbolic regression, get multiple hypotheses. Here's R, F1, till F7. Here's another one, G1 to G7. But then you ask which one of them is also consistent with anything that can be derived. It's an implicit form. You end up only with a specific expression, right? Which is this G2, I believe, and F2. Right? Now to Einstein time dilation problem. So as I hope most of you know, right? Time is experienced differently depending on the reference system that you are in. And what we wanted to do in this exercise is to contrast two different axiomatic systems, and to see whether we can tell them apart. So here are our heroes, and the difference is really this equation, right? The classical mechanics one would assume that the speed can be added, right? So v squared plus c squared, and Einstein would simply say no, you cannot exceed the speed, right? And we found indeed that that consistency, and you can ask. We wouldn't actually with this system we couldn't discover the true relation. We found an approximation of which, but we asked a different question. If we bound the reasoning error to some extent, what would be the largest range in which a certain theory would hold? Right. So that was another thing that you can ask yourself and play with now. So if you're curious, this work was published recently in Nature Communication. There is open source code. So if you have your own. If you would like to have your own Nobel Prize, you can go, download it, bring your data and knowledge, and there is a price, I have to tell you. You have to buy me beer if you get it. But other than that, no other royalties. So it's relatively cheap as a mean to get Nobel Prizes. Now, if I summarize what we've seen so far, we have I would say the king of the jungle these days, which are probably neural networks, and typically they have fixed functional form, and all that we can tweak are some parameters in this. So taking maybe one step forward, we went, and so what happened when we freeform? We try to make discoveries with symbolic entities. That was a step, hopefully in the right direction, but then we wanted to bring the theory in, and the background theory in, and then we looked into this symbolic regression and certification. So coming up with a set of hypotheses and then having a gatekeeper in the form of formal logic to see which one of them is more consistent or less consistent. But wouldn't it be so much nicer if we will not do that as a pipeline? First, come up with propositions, then qualify them. Can we somehow bring partial, noisy data, small data on the one hand, and then bring incomplete, even inconsistent knowledge on the other hand, and find that place where the two can actually connect and tell us something that we didn't know, right? This is what we would like to do. And the last part of our work was really trying to pursue that, right? So we would like a unified framework that brings everything together, bring the theory and the data and the complexity into one optimization problem. Now, to qualify the fidelity of the data, we all know how to do that. This is, there are many ways, many different noise models. I cannot really tell you anything new in that domain. Same even for complexities. There are different ways to define the complexity of a model. I will not qualify that any one is any better than another. There are different ways to do that, right? So, but really the challenging question is, how do you bring numerical values and symbolic expression into a single space where they can talk with each other and exchange value? That was the challenge. So we couldn't do that for all, like completely universally, but one really interesting theorem that we found that can take us very, very far, I believe, is due to David Hilbert, and it's called the null-Stellensatz, later on the positive Stellensatz proposition. And what that statement is saying is, imagine that you have a set of polynomial equalities and inequalities. And these are multivariate polynomials. Now, with that you can actually, so this is called a semi-algebraic set, and with that you can actually represent a large body of problems. Polynomials are very expressive, they are actually very traceable, very easy to differentiate them, to do a lot of manipulations with polynomials. The nice thing is that you can, with that statement, there are actually two options, right? So either there is a solution, so the question is there a solution to that problem? And if there is a solution, that's easy. Give me the solution, I can check that, great, problem is solved. But if there isn't a solution, can you provide a certification that nowhere of possible x's that equation or that system of equations will be satisfied? And that's an NP-hard problem. NP problem, sorry. No, it is an NP-hard problem. It is decidable. But the beauty is that with this framework, you can actually, maybe I will not take you, so here's one of those versions. It's called Potinar, positive Stellensatz theorem, and it is based on something called sum of squares. It is not to the light-hearted, but it's not that complicated as it may seem. First, I will not take you into the hairy details of that, but at the end of the day, with this machinery at hand, you can take that problem that otherwise would be NP-hard and solve it, turn it into a polynomial optimization problem that is convex, and then solve it very, very effectively. Right? So you can solve it as a semi-definite program. And So how does it look like with all of those terms? So when I say polynomial expression, I'm not looking for a spline approximation for my solution. So this could be the mathematical model, right? So it can be an implicit representation of the model. This one is the Kepler that we just saw before. Here is the background theory that is represented indeed with these polynomials. These are apparently polynomials. And what you see in red is the certificate. So these are multipliers that when you multiply them with the background theory, you would get the discovered expression that you have. And the moment you have that, you actually have a certificate, proof for your discovery. And here is just a very high level description of the framework. You can come up with noisy data, some background theory, even incorrect theory, some hyperparameters. Always put that into a polynomial program, convert that into a semi-definite program, and then you get a symbolic model and proof of derivability, and that is scalable. And here are some examples. So can you do differential equations? A question that we are being asked often. And here is an example of the Hagen-Poisson-Wheel equation, which is an approximation to the Navier-Stokes equation in certain geometries. I will not bother you with the heavy details, but this is definitely discoverable. Let's push it up a little bit even. Radiation gravitational wave equation. Slightly more intimidating expression in some regards. You have a third derivative in time if you look into the middle of that race. Kepler law is the first one. The gravitational power wave equation, a quadruple moment tensor, all of those things come into play, and you can really make the discovery of the expression. It is nice to visualize the background theory and the intersection of those, and you can do that actually with that representation. So that's quite pleasing for the eye, at least for me. And then we were challenged. Okay, well, what about quantum mechanics? Can you do something in that space? So back to my personal ambition to get a Nobel Prize. We managed to get as far as last year. So my ambition is to go to 2024, not 2022. I'm on it. But Bell inequalities, for those of you who are not familiar, they effectively provide a bound to the correlation of measurement of multi-particle systems that obeys local realism, and you would like to show that they are violated, and that was a big discussion between Einstein, Podolsky-Rosen, and others. So we managed to do the first, the non-GHZ inequality. And just to be fair, the Nobel Prize was not awarded for the theoretical work. It was actually awarded for the empirical validation of which, just to be completely fair here. But then we said, okay, can we push it up? So then we took more challenging Bell inequalities as this I3-3-2-2 inequality, and it can be done in a breeze, right? So you can also discover these relations. So maybe to summarize the three frameworks that I suggested. So we are talking about the scientific discovery cycle, and I believe that we would like to scale the scientific method, and to do that we need a disruptive new paradigm. We cannot just keep on doing what we did yesterday, so we cannot use yesterday's algorithm with tomorrow's computation and hope that everything will just work. We need a paradigm shift in how we go about it. And if we take just a small segment of that discovery cycle and look into the hypothesis generation and the data testing, which is typically what we do in classical scientific discovery, machine learning tells us, oh, you know what? Let me do the hypothesis generation. I will come up with some proposition, and that's great. What we did with the AI Descartes was effectively saying, you know what? Let's go with what you propose, but let's also bring the theory, the logic, to reason and ensure that what you found, of all that you found, which one of them is more consistent. But then maybe the next step is how can you do that at the same time? I don't want to come up with multiple propositions and then qualify and go back and forth. I would like to somehow synthesize them together, and that was the latest work of the AI Hilbert, that we generate hypotheses that are already consistent with the data. And both parts are maybe missing, but together they can complement each other. And so all in all, hopefully I try to show you that we have a path, or at least one path. There are many other better, nicer, it depends on your perspective, proposition maybe that can come or will come to do that, or ever have come. But there is a path, I believe, to accelerating the scientific discovery effort. We would like to come up with relations that are universal. They are derivable, not only interpretable. Interpretable is great, but derivable is even better. We would like to be able to make discoveries when we have small data, and that data can be noisy, and similarly, we may have small, imperfect knowledge, and we would like to be able to bring all of them into the same place. For now, maybe the task is to be an adjunct to human scientists and aid them. We don't know what, how far the system can go. At some point, they would say, "Why do I need this gray hair guy? Let me do everything myself, right?" But for now, let's use it as an adjunct. And I hope that this is a step forward for us to be able to make discoveries that are outside the realm of everything that we can do just with our own capabilities. So I would like to thank you very much for listening. And if you have any questions, I'm here.
Prerogative of the host and ask the first question, which is, you've mostly phrased this in the language of sort of regression, or you've got the data already, what are you going to do with it? It seems interesting to poke at this in two ways. One is the suggestion of new experiments. The other one is, when you were showing the Kepler approximation, for example, I looked at that and said M1 and M2 should play a symmetric role. That's something that's not captured. So is there feedback mechanisms either envisioned or in the current system for asking questions about new experimental data, or for a scientist to say, please add the following restriction or invariance, or that you may have missed before?
I love both questions. So on the first one, I have an easy answer. Let me see if I can find it. I believe, if it's not here, yeah, we had a recent archive on optimal experimental design in the setup where you have both data and model forms that you are trying to, parameters and model forms that you are trying to discover. And it's a more interesting and challenging proposition, because we typically either do one or the other. The second question, I think that this is the sort of paradigm shift that we are looking for, right? So how can we keep on challenging ourselves or the system to ask those questions that are non-trivial, right? So we can do it with a multi-agent setup where, similarly to we mentioned Hilbert and Gödel and others, we're exchanging letters of here I managed to prove this one in 6 steps. Can you do it in 5? We need to have a multi-agent system that can challenge and ask about, okay, how about symmetries, or can I come up with new set of hypotheses? Because we discussed it earlier. Einstein relations didn't come out from taking Newton laws and just shuffling them, right? You really have to say, you know what, interesting, but let's come up with a new postulates, and let's see if I can make those work for me in the sense that they will honor everything that we know so far, but also be able to predict something surprising, interesting, exciting that we didn't see so far. I think that we need to think about maybe adaptive logic as a form of the equivalent of experimental design. So how can we propose a new axiom or set of axioms. The same way that you propose another way to collect data, and the two would be very nice ways to extend the framework beyond that, because all that we did was actually touching one segment of this full cycle, and you're absolutely right. There are other important parts that needs to be addressed.
Alex.
Thank you for the nice talk. I was just wondering if your symbolic regression or any of the tools you presented today can get the right coordinate space. So let's say if we're in the Kepler laws, we're going to collect data in an Earth-centric model. But really the nice model comes from a sun-centric model. And can your systems, do you have any way to be able to get into the right coordinate space to get a simple model?
Yeah, excellent question. So first of all, there have been very nice work, I believe, by Nathan Kutz and other, specifically targeting that element. So incorporating a numeral component that was learning some coordinate transformation. So this can be done absolutely. In our case, we literally said if there is such a transformation, I didn't ask my model to come up with a discovery that is with pre-processed data. So we, for instance, for the pendulum, we took the raw data. It was actually from a phone. We took a phone on a high-speed video, and we took the data as is without coordinate transformation or anything, and we managed to discover the relationship.
But does your symbolic dictionary there contain theta or contain the primitive variables?
So we only have, you ask a very important question. So on the one hand, we only have the data of what is observable, but the model can incorporate parameters that are latent, right? So they are not part of, especially if you have theory, right? So there may be some relations that I may not see in the final derivation, but are actually playing a role, and that can be done, right? So coordinate transformation can be a good instance of which, right? Because you are performing some Jacobian type of transformation of coordinates, and you end up with a new set of coordinates, but thereafter, like, who cares? You really care about the relation and how it works. But maybe an interesting question would be, how can you decompose and understand that this component, all that it did was actually bringing the coordinates into a certain form, and then the rest is attending to other forms of the behavior of the system. Right? So it's a very interesting question.
So thank you very much for the talk. Just a real quick one. If I consider the idea of encoding background information into the methods that you're proposing, what if I'm doing something like Newton's first law of motion, the inertia question? Can I encode something like that into a formal mathematically tractable?
Yeah, absolutely. So Newton laws, we actually did that in one form or another in some of those discoveries. So that those 100 relations that are in Feynman's lectures on physics. Some of them include obviously Newton laws in different form. So absolutely yes, we can encode those relations.
I mean, like, some things are uniquely still expressible only in natural language, not mathematically expressible. This is what I mean.
I see. So this is one maybe missing part of because I'm sure that many scientists, they have that knowledge expressed in natural language.
Yeah.
And big challenge that I think we have, we spoke slightly about it earlier, right? Is how can we come up with knowledge sets, right? Because as a community, we all feel comfortable. There is a data set and another data set, but we need one maybe few unified knowledge sets where we curate and standardize the language in which we use to articulate many of those relations, and then we need those mediations, right? So maybe generative AI can help us to take a description, a lingual description of a phenomena from a practitioner, translate it into those primitives of
like
relations.
like we need a compiler or something.
A compiler, like,
Okay.
yeah, exactly.
So I can see that there's lots of additional questions. We are 5 minutes past what we said. So I'm going to suggest that we thank Liam again and then move over to, or Lior, then move over to the camp space and talk further over food.